Since this is the first lecture, I will briefly describe what I'm going to speak about. So first we discuss the notion of Gaussian measures on Banach spaces. We will start with things that you may know, Gaussian measures on finite dimensional spaces. We will define what is the Ornstein-Uhlenbeck semigroup, discuss some properties of this semigroup and in particular the concavity properties of Gaussian measures. Also, we will discuss the Kakutani theorem. The second part of the course will be devoted to the structure of Gaussian measures. In particular, we will discuss what is the Cameron-Martin space, properties of equivalence and singularity of Gaussian measures, and the notion of measurable linear functions. And the last part will be devoted to transformations of Gaussian measures. We will study linear transformations, also how Gaussian measures change under linear transformations, in the sense that what linear transformations are absolutely continuous. Also, we will need the notion of Sobolev functions. And finally, we will discuss nonlinear transformations and some applications. So I mainly oriented on the following books. So there are monographs by Bogachev, Lifshitz, Adler, and of course, many others. Okay, so let me recall what is a Gaussian process is. A family of random variables that are defined on some probability space is a Gaussian process if for any finite number of indices t1, tn, the random vector xt1, xtn is Gaussian. This means that the characteristic function of this vector, so expectation of exponent I times the sum lambda j xtj, has the following form. This is the exponent of ia lambda minus 1/2 a lambda lambda. So here A is some n-dimensional vector. A capital is a symmetric non-negative definite matrix of size n. When we have such expression for characteristic function, we can deduce that actually A is the vector of expectations. xt1 till expectation xtn. Okay, and the matrix A is actually the covariance matrix of the vector. So it consists of covariance, let's say xtj, xtk, where j and k change from 1 to n. Okay. And if the matrix A is non-degenerate, then the vector xt1, xtn has the probability density function, and it equals the following expression. So here 1 over 2 pi to the power n over 2 root of the determinant of A times exponent and here minus 1/2. So this is the quadratic form of the inverse matrix of A. Okay, so this is the notion of a Gaussian process, and now I want to say a few words why they are important. Firstly, the structure of a Gaussian process is mainly determined by its covariance function. As a result, a lot of characteristics of Gaussian processes then can be either found explicitly or they can be described in a relatively simple way. Most importantly, Gaussian processes naturally arise as limiting objects in many complicated models. For example, you all know the central limit theorem that states that if we have a sequence of independent, identically distributed random variables, say with expectation 0 and variance 1, if we take the sum, divide by root of n, then we will get in the limit the standard Gaussian random variable. Also, you may know Donskir's invariance principle that states that if we have a random walk, then after proper rescaling, we can get in the limit the Brownian motion, which is a Gaussian process. Also, of course, Brownian motion is important because it is used to define stochastic differential equations and diffusion processes, and a lot of a lot of theories that are under development now, they are based on the theory of Gaussian processes. One can mention stochastic flows, stochastic loaner evolutions, theory of regularity structures, and so on. So this, what I thought, can be a motivation to study Gaussian processes. And we will do this by studying actually Gaussian measures. So a Gaussian measure is the distribution of a Gaussian process in some space. We will look at Gaussian measures from the point of view of functional analysis, from the point of view of measure theory, and so on. Okay, so let's define what is a Gaussian measure. We will start from one-dimensional case, which is the simplest one. So a probability measure on the real line is called Gaussian if the Fourier transform of this measure has the following form. So I denote the Fourier transform by gamma hat of t. This is by definition such integral, the integral of exponent itx d gamma x. And the Fourier transform must have the form exponent iat minus 1/2 sigma squared t squared. So here, where a is a real number, sigma is non-negative. So if sigma is bigger than 0, then the probability measure gamma has a density with respect to Lebesgue measure, and this density equals 1 over root 2 pi sigma squared exponent minus x minus a squared divided by 2 sigma squared. If sigma is equal to 0, then we have the Fourier transform of the form exponent iat. And this is exactly the Fourier transform of the measure that is concentrated at a point A. So the measure gamma of a set B will be just 1 or 0, depending on whether A belongs to B or not. Okay, if A is equal to 0, sigma is equal to 1, the Gaussian measure, I will denote it gamma 1, meaning that this is the standard Gaussian measure. Also, I note once again then that A is just the expectation. So this is the integral of x d gamma x, and sigma square is the variance of the measure. So this is the integral of x minus a squared d gamma x. Okay. Now we give a similar definition of a Gaussian measure on the n-dimensional space. So a probability measure on Rn is called Gaussian if its Fourier transform has the following form. So the Fourier transform of gamma must be of the form exponent I a lambda. So this is the inner product, yes, minus 1/2 a lambda lambda. So this is the quadratic form of some symmetric non-negative definite matrix of size n. Again, A equals the expectation of the measure. So this is the integral of y d gamma y. And the matrix A consists of covariances of different components of y, meaning that aij is the integral of yi minus ai times yj minus aj d gamma y. Okay, now if the vector A is equal to 0 and A capital is the identity matrix, then the corresponding measure will be denoted by gamma n. So this is the standard Gaussian measure in n-dimensional space. And we can also know that the standard Gaussian measure in n-dimensional space is the product of one-dimensional Gaussian measures. This is just the consequence of the fact that the Fourier transform of gamma n, this is exponent minus 1/2 a is identity, so lambda lambda, and this is the product of exponents minus 1/2 say lambda k squared, and k goes from 1 to n. So this is the product of Fourier transforms of one-dimensional Gaussian measures. Okay. Now there is an equivalent definition of a Gaussian measure, which we will actually need. So I give it now. A probability measure is Gaussian if and only if for any linear functional on n-dimensional space, the distribution of this functional with respect to the measure gamma is a Gaussian measure on one-dimensional space. Okay, so gamma is a probability measure on Rn. Gamma L minus 1 is a probability measure on the real line. So gamma is Gaussian if and only if all these probability measures are Gaussian measures. So let's check that this is indeed the equivalent definition of a Gaussian measure. So first, assume that gamma is Gaussian. This means that the Fourier transform of the measure gamma is equal to exponent I a lambda minus 1/2 a lambda lambda. Now consider some linear functional which necessarily has the form of inner product of y with some vector. And let's look at the Fourier transform of the image of the measure gamma. It is equal to the integral over real line exponent itx with respect to the image measure. Okay, so since we integrate over the image measure, this is the same as the integral over Rn e exponent I t, and here instead of x we write L of y, which is lambda y. Okay, but then this is just the Fourier transform of gamma at a point t lambda, which is equal to exponent I t a lambda minus 1/2 t squared a lambda lambda. And we get the Fourier transform of a Gaussian measure. Okay, so if gamma is Gaussian, then all linear functionals are distributed as Gaussian measures with respect to gamma. Now, conversely, let all measures, all image measure, all distributions of all linear functionals with respect to gamma be Gaussian. Let's consider the following vector ai, which is so ith component of a equals to the integral yi d gamma y. And consider the matrix aij, which has the following components: integral yi minus ai, yj minus aj d gamma y. If lambda is some vector, define the following linear functional L lambda of y, which is equal to the product of lambda and y. And we know that this functional is distributed with respect to gamma as a Gaussian random variable. Okay, so its Fourier transform which is equal to the integral exponent I t lambda y, must have the form exponent I t times some number, which depends on lambda, minus 1/2 t squared times some number which also depends on lambda. But we actually know what is a lambda. So since a lambda is the expectation of gamma, it means that a lambda must be equal to the inner product of a and lambda. And since sigma squared of lambda is the variance, we must have that sigma squared lambda is a lambda lambda. So as a consequence, we get that the Fourier transform of gamma, which is just equal to the Fourier transform of the image of measure gamma at point 1, equals to exponent I a lambda minus 1/2 a lambda lambda. Okay. In this way, we have two equivalent definitions of a Gaussian measure on n-dimensional space. So it can be either defined by its Fourier transform, or it can be defined as a probability measure such that any linear functional is distributed as a Gaussian random variable with respect to this measure. Actually, the second definition we will take as a definition of a Gaussian measure in a more general spaces. Actually, we will define what is a Gaussian measure on a Banach space. And it will be a probability measure such that every linear functional is distributed as a Gaussian random variable. Actually, every continuous linear function. Okay, now I will define two important objects related to Gaussian measures. So first is a Hermite polynomial. The kth Hermite polynomial is defined by the following expression. So this is minus 1 to the power k divided by root of factorial k exponent x squared over 2. And here the case derivative of exponent minus x squared over 2. And such polynomials are defined for k equals 0, 1, 2, 3, and so on. This is indeed a polynomial of degree k, and its leading coefficient equals 1 over square root of factorial k. Okay, and the n-dimensional Hermite polynomial is defined for any multi-index So alpha contains of n natural numbers, and h alpha is defined as hk1 of x1 times and so on times hkn of xn. So this is the polynomial on Rn, and degree of h alpha equals k1 and so on plus kn. Okay. Hermite polynomials can be obtained from the following expansion. So for all lambda and x, we have the following equality. So exponent lambda x minus 1/2 lambda squared is equal to the sum of the following series. So it's lambda to the power k divided by root of factorial k and times the kth Hermite polynomial. This can be obtained as follows. Consider the following function. And for a fixed x, let's write its Taylor expansion in the powers of lambda. So this will be lambda to the power k divided by factorial k. And here I must write the case the derivative of this function when lambda is equal to 0. But when we differentiate this exponent, this is the same as differentiate just exponent minus 1/2 x squared, but we will obtain -1 to the power k. Okay. And what remains is to know that exponent lambda x minus 1/2 lambda squared, this is the same as series, but with multiple exponent x squared over 2 divided by factorial k. So here we see that this is exactly the case Hermite polynomial. Okay, so we get such expansion. If we differentiate this expression with respect to x, then on the right hand side we will get the sum of the series with hk prime of x, and on the left side we will get a multiple lambda. Okay. Then we can write it as follows. So in fact, the sum is not from 0, but from 1, because h0 is 1. This is lambda times the sum k from 0 to infinity, lambda to the power k divided by factorial k plus 1 square root h k plus 1 prime of x. And what we have on the left is lambda sum k from 0 to infinity, lambda to the power k divided by factorial k square root hk. Now, if we compare coefficients near the same powers of lambda, we get that h prime k plus 1 x divided by k plus 1 factorial square root is equal to hk of x divided by k factorial square root. So we get this equation. Hk prime equals to root of k times hk minus 1. Okay, so this is one recurrence relation. And another one is that hk prime actually equals to x hk of x minus root of k plus 1 hk plus 1. This can be obtained just from the definition. So we defined hk as minus 1 to the power k divided by the root of k factorial exponent times the case the derivative of exponent minus x squared over 2. Okay, and now let's differentiate this. When we differentiate exponent, we just get the multiple x. Yes. When we differentiate exponent x squared over 2, we get x times this exponent. So we will obtain x times hk of x. And when we differentiate the case, the derivative of the exponent, we get minus 1 to the power k divided by k factorial exponent. Here we will get k plus 1. So for this to become k plus first Hermite polynomial, we just miss the factor 1 over root k plus 1, and we miss a sign. This would be minus. So we obtain one more recurrence relation. So either we can say that hk prime of x is equal to this difference, or we can say that root k plus 1 hk plus 1 of x is equal to x hk of x minus root of k hk minus 1 of x. So since h0 is 1, h1 is x, then we can just compute all other Hermite polynomials. Okay. These polynomials are important because they form an orthonormal basis in L2 space with respect to the standard Gaussian measure gamma 1. Why they are orthogonal? Let's see. So let's integrate hk with x to the power n with respect to the standard Gaussian measure gamma 1. So hk of x is -1 to the power k divided by root of k factorial. Also, I write here 2 pi, which comes from the density of gamma 1. Then we will have the integral exponent times the case derivative of exponent minus x squared over 2 times x to the power n and times the density of gamma 1. So these two exponents cancel. And now what we can do, we can just k times integrate by parts here. So after if n is less than k, then after n plus first integration by parts, we will get just 0, because x to the power n will disappear. Okay, and if n is equal to k, then after k integration by parts, we will get 1 over root 2 pi k factorial, the integral of e minus x squared over 2 dx. And also, when we integrate by parts, we will get multiples like k minus 1, and so on. So we will get factorial k. So this is equal to the root of the factorial k. So we see that the polynomial hk is orthogonal to all polynomials of the power less than k. This already proves that two Hermite polynomials of different power are orthogonal. And if k is equal to j, then we can write the integral of hkx times hkx as 1 over root of k factorial x to the power k plus some linear combination of powers of x less than k. And from here, we get that this is 1. So we see that the sequence of Hermite polynomials is an orthonormal sequence in the space L2 with respect to the standard Gaussian measure. Also, note that the polynomials are dense in this L2. This is the consequence of the fact that expectation, the integral of exponent alpha x d gamma 1 of x is finite for all alpha. So as soon as you have a probability measure such that all exponents are integrable with respect to this probability measure, then polynomials will be dense in L2. In fact, if some function f belongs to L2 gamma 1, and if f is orthogonal to all polynomials, then we consider the Fourier transform of f. So this is the integral I, let's say zx f of x d gamma 1 of x. Now this is well defined because of this condition, and actually this is entire function. Since f is orthogonal to all polynomials, this entire function will be equal to 0 together with all the derivatives of f. But this means that the entire function is equal to 0 for all z, so the Fourier transform of f is equal to 0, so f is equal to 0. This shows that if a function is orthogonal to all polynomials, then it is equal to 0, which actually means that polynomials are dense. Okay, so we have defined a sequence of Hermite polynomials, and we show that this is an orthonormal basis in L2 with respect to the standard Gaussian measure. It follows then if we define, if we consider H alpha, I recall that H alpha of x is equal to the product Hkj of xj, j goes from 1 to n, then this will be the orthonormal basis in n-dimensional space with the standard Gaussian measure. By xk, I will denote the span of n-dimensional Hermite polynomials for which the sum k1 plus kn is equal to k. So this is the span of all n-dimensional Hermite polynomials of degree k. And since H alpha form an orthonormal basis in L2, then we can represent L2 space with respect to gamma n as the orthogonal sum of subspaces xk. Here must be from 0 to infinity. And then by ik, we will denote the orthogonal projection on the subspace xk. This is the first instance when the so-called chaos expansion appears. So the representation of the subspace of the space L2 as the orthogonal sum of subspaces xk will appear in the future in the for Gaussian measures on Banach spaces, and we will call it the chaos expansion. So as an example of decomposition of the function f into the sum of orthogonal elements. So let's take the function which is infinitely differentiable and such that all the derivatives of this function are square integrable with respect to the here I consider gamma 1. So with respect to the standard Gaussian measure on the real line. Then actually we can compute the inner product of f and hk, and it will be equal to 1 over the root of factorial k of the integral of the case the derivative of f. Indeed, this inner product is the integral f of x. Now what is hk? It's minus 1 to the power k divided by root 2 pi factorial k and times the case the derivative of exponent, and also times exponent to the power x squared over 2, but we will also have the density of gamma 1, so this will be just dx. And now after we integrate by parts k times, we will get 1 over square root 2 pi k factorial integral of the case the derivative of f x times exponent dx. So this is exactly the integral of the case derivative of f with respect to the standard Gaussian measure and with the multiple 1 over factorial k. You may ask me, and actually you should ask me, why it is allowed to integrate by parts here, because we integrate over the whole real line. So this is a technical question which can be solved in the following way. So we take some infinitely differentiable function with a compact support, and we can take it in such a way that phi is equal to 1 when x is less than 1 and phi is equal to 0 when x is bigger than 2. Okay, and then define the function fr as the product of f and phi x over r. Note that this is equal to f of x when x is less or equal to r, and it is equal to 0 when x is greater or equal to 2r. Now the function fr has a compact support. So here it is legitimate to integrate by parts. And now we just take the limit when r goes to infinity. Note that fr converges to f in L2. And in fact, all the derivatives of fr, they also converge to corresponding derivatives of f in L2. So this means that this converges to the inner product of f and hk, and this converges to 1 over k factorial inner product of fk and 1. And we get such nice series representation of the function f. So it is written as the sum of orthogonal polynomials. Okay. The next object I want to introduce is the Ornstein-Uhlenbeck semigroup. It is defined for any centered Gaussian measure. So gamma is a centered Gaussian measure on n-dimensional space. Centered means that A, which is the expectation, is 0. So the Ornstein-Uhlenbeck semigroup is defined on any space LP with respect to gamma by the following expression. So TTF of x is the integral of f. Here the argument of f is exponent minus t times x plus square root of 1 minus exponent minus 2t times y. And we integrate it with respect to y. Of course, the correctness of this definition must be checked. And this definition is correct because of the following property. Consider the product of two measures, gamma and gamma. So this is a measure on Rn times Rn. And consider the mapping that takes two n-dimensional vectors, so x, y, both belong to Rn, and send it to the vector e minus tx plus root 1 minus e minus 2ty. This is the vector in Rn. So under this mapping, the product gamma times gamma is sent into some other measure, let's say mu. So mu is the image. Now let's find the Fourier transform of mu. This is the integral of over Rn, exponent I lambda, let's say that, d mu. Since mu is the image of gamma times gamma, this is equal to the integral over Rn exponent I lambda e minus tx plus root e minus 1 minus e minus 2ty d gamma x d gamma y. But now we can write exponent as the product of two exponents, one with x, one with y. So we will obtain the Fourier transform of gamma at the point e minus t lambda times the Fourier transform of gamma at the point root 1 minus exponent lambda. Okay, but what is this? Gamma is a centered Gaussian measure, so this is exponent minus 1/2 e minus 2t a lambda lambda times exponent minus 1/2 1 minus e minus 2t a lambda lambda. So altogether we get the Fourier transform of gamma. So this means that actually the measure mu coincides with gamma. Now, if we take f in LP with respect to gamma, this means that the integral of absolute value of f to the power p d gamma is finite. But from our considerations, this can also be written as the integral of f e minus tx plus root 1 minus e minus 2ty to the power p d gamma x d gamma y. And since this double integral is finite, by Fubini theorem, we deduce that actually for almost all, for gamma almost all x, the integral of absolute value f e minus tx plus root 1 minus e minus 2ty d gamma y is finite. And in particular, we can integrate f. So this shows that this integral is well defined for almost all x. Also, if we take the power p of this integral and integrate with respect to x and use the Hölder inequality, we will obtain that dtf absolute value to the power p integral d gamma less or equal than the integral of f to the power p d gamma. So operators tt, they act in all spaces LP, and moreover, the norm of the operator t actually is equal to 1. It is less or equal to 1 because of this inequality, and f and operators send the function which is equal to 1 into itself. Okay, so we get a family of operators that act in LP. And actually, these operators form a semigroup in the sense that if we apply TS and then we apply TT, this is the same as we apply T plus S. Okay, so let's check the semigroup property. This is the integral TSF e minus tx plus root 1 minus e minus 2ty d gamma y. Now substitute ts. We will have the integral of f e minus s e minus tx plus root 1 minus e minus 2ty plus root e minus 2s, let's say z d gamma y d gamma z. And let's write it as follows. Okay. Plus I write here root of 1 minus e minus 2s plus t. E minus s root of 1 minus e minus 2t y plus e minus 2s 1 minus e minus 2s root divided by 1 minus e minus 2s plus t. And this is d gamma y d gamma z. Now the idea is that sum of squares of these coefficients is equal to 1. And as we saw, if this is the case, then the product gamma times gamma under such mapping is sent to the measure gamma. So we can write it as the integral over the image of the measure. Which is the definition of operator tt plus s. So this is indeed a semigroup. This semigroup is strongly continuous in the sense that if the function f belongs to LP, then TTF converges to f in LP. If we take a bounded continuous function, then TTF is the integral e minus tx plus root 1 minus e minus 2ty d gamma y. And when t converges to 0, then just this function, the expression under the integral just converges to f of x. If f is bounded, we use the dominated convergence and deduce that the convergence will be in LP. Also, bounded continuous functions are dense in LP, and as we saw, the norm of the operator tt is equal to 1. Yeah, so if we consider any function f in LP, we find a bounded continuous function g such that the distance between f and g less than epsilon, I mean the distance in LP, then we estimate TTF minus F as follows, as TTF minus TTG plus TTG minus G plus G minus F. And now this is less than epsilon. This is also less than epsilon because the norm of TT is equal to 1. And since G is bounded and continuous, this converges to 0. So we see that this will also converge. Okay, and next is property that TT is symmetric and non-negative on L2. Maybe I will not go into details very much, but here the main idea is that we can consider the measure gamma times gamma, and this is a measure on Rn times Rn, and map it into another measure on Rn times Rn in the following way. Then actually the Fourier transform of the image can be found, and it is the same as the Fourier transform of gamma times gamma. So this means that this transformation sends the product measure gamma gamma into itself. As a consequence, we have the equality, which means that actually TT is a symmetric operator. This immediately implies that it is non-negative, because we can write TT as T over 2, T over 2, F. Then we apply the symmetry, yes, and get that this is the square of the norm of T over 2F, which is bigger than 0. So we get symmetry and non-negativity properties. Okay, and if gamma is a standard Gaussian measure, then the action of the semi-group is quite simple, so it can be written as the sum. Okay, so I recall that Ik is the projection of f onto the space of polynomials of degree k, and each such projection is just multiplied by exponent to the power minus kt. To prove this, it is enough to consider the case when n is equal to 1, because then when n is bigger than 1, then gamma n is just the product measure, and this equality immediately follows. So let's write what is our semigroup. This is the integral And let's substitute the case Hermite polynomial instead of f. So hk is a polynomial of degree k with the leading coefficient 1 over root of k factorial. If we expand this into the powers of x and powers of y, we will get a polynomial of degree k. So, I mean, after integration with respect to y, we get a polynomial of degree k in x. The leading coefficient will be equal e minus kt divided by the root of factorial k. Okay, and let's note that the inner product of TTHK and, let's say, P. So if P is a polynomial of degree less than K. By symmetry, this is equal to the inner product of HK and TTP. But if P is a polynomial of degree less than K, then this is also a polynomial of degree less than K. And HK is orthogonal to all such polynomials. So we see that the action of the semigroup on the Hermite polynomial gives a polynomial of the same degree, which is orthogonal to all polynomials of smaller degree. This means that it must be proportional to K's Hermite polynomial. But the leading coefficient of HK is equal 1 over root of K factorial, and leading coefficient of TTHK is has additional multiple exponent. So we find the action of our semigroup on all Hermite polynomials. So this means that on the case subspace xk, TT acts as a multiplication by E minus kt. Okay, and the last notion that I will give today is the notion of the Ornstein-Uhlenbeck operator. So it is defined as a generator of the semigroup. So the domain of this operator consists of all functions f for which the limit exists. And on this domain, the operator L is defined as this limit. The domain of the operator can be described. In fact, it consists of all functions for which the sum is finite. So this is the sum of k squared times the norm of kth projection of f squared. And also the action of L is equal to minus the sum of k ikf. If f belongs to the domain of L, then okay, we can then there exists the derivative of TTF at 0, and it is equal to LF. Now, if we apply the projection operator, we will get derivative of IK TTF, but we know what it is. This is E minus KT IKF. So we get minus K IKF. As a consequence, this must converge, and also we actually find what is LF. So on kth subspace, it acts as a multiplication by minus K. Okay, and conversely, if the sum is convergent, then we can just prove that this converges to 0, because this expression equals to the sum. Okay, if we expand f into orthogonal subspaces, then TT acts as a multiplication by exponent. Again, since this is an orthogonal expansion, we get here squared. Remove this thing and put square here. Okay, so by the dominated convergence, this converges to 0 when t converges to 0. Okay, so in this way we find actually the domain of Ornstein-Uhlenbeck operator and how it acts on functions from its domain. Of course, this expression is not very clear, maybe, but next time we will show that LF has another representation as a Laplace operator minus the product of x and the gradient of f. So this gives the connection of operator L and some parabolic equations. And also we will prove important properties of Ornstein-Uhlenbeck semigroup, such as hypercontractivity. we saw that the norm of Ornstein-Uhlenbeck semigroup in every LP is equal to 1. But hypercontractivity means more. Actually, Ornstein-Uhlenbeck semigroup sends the space LP into space LQ, where Q is bigger than P. So it improves the integrability properties of functions. So we will show this property, which is called hypercontractivity, and also we will look at concavity of Gaussian measures. Okay, also I hope we will have time to give a definition what is a Gaussian measure on Banach space and look at some examples. So this is the plan for the next lecture. So please, if you have any questions, you're welcome. So no questions?